welcome to the course on two-dimensional signal processing principles and practices. So, we are doing the signal processing overview, and we have done this classification of signals and the classification of systems we are doing, and we did this linearity property of the systems. So, we look at the details of this in the discrete time systems. So, the linearity is defined that the class of systems for which the principle of superposition and homogeneity needs to be satisfied. So, when in the case of superposition, we take the input x of n and give it to the system, so get y of n, and the system input, the other input x2 of n is passed through the system and giving the output as y2 of n. So, how when we get the responses as y1 and y2, if we combine these two inputs x1 of n and x2 of n, then what should be the output of the system? That should be y1 of n plus y2 of n. That is what the superposition theorem says. So, here if we take this in the equation, h of x1 of n plus x2 of n, that is combined input where the system is acting on this combined input, it is equivalent to saying that system is acting on individual inputs h of x1 of n, h of x2 of n. So, that is addition of this two. So, which is equivalent to the output what we get is y1 of n plus y2 of n for both these cases. That is what the superposition theorem is about. So, x1 individual input response is equivalent to the combined input response. This is for the superposition theorem, whereas the homogeneity, if we include it in the linearity property of this system. So, a scaling, the input is scaled a x of n, and the output from the system is obtained by system acting on this input h, it is equal to a h of x of n here. So, the output is now simply y of n is multiplied with the scaled constant or the constant equal to a. So, a into y of n. So, these two properties are satisfied, then the system needs to be said to be linear. That is for this, we have shown it for the continuous time system. For the discrete time system, this n, you can notice the n which is valid for only some certain time instance which is integer here. And taking the time invariance property of the system like we did for the continuous time system, this is extended to the discrete time system where h is the system operator acting on the input x of n which is applied to it and give the response as y of n. Once we obtain this y of n and delay it for a certain time units, then get the y of n minus n. So, the system response is now y of n minus n. But instead of giving this x of n directly to the system, so delay this input x of n for a certain time units, that is x of n minus n. After that, give to the system, that is same as in the case of this continuous time system what we did. So, that here x, then that would give the response as y of n minus n. So, if both the inputs these inputs and the way in which it is coming from here to here and here to here would yield the same responses. So, this if both are same, then the system is going to be time invariant or shift invariant systems. If not, then it is going to be time variant or shift variant systems. So, if these two are not equal, then it is going to be time variant or the shift variant systems. Now, coming to the analog and digital systems, which is going to be system input and the output are analog. In case of analog system, the input and the output both are analog, that means analog signals. And for the digital systems, the system input and the output both are digital. That means we had seen in the previous lecture, the digital signal is that going to be ones and zeros. So, the system input is also ones and zeros and the output is also here going to be ones and zeros. So, this would be analog input where the system input is continuous in time and continuous in amplitude. Similarly, the output as well, continuous in time and continuous in amplitude in case of analog systems, and this is for the digital systems. Now, this another classification is invertible and non-invertible systems. So, whether the system is invertible or not. So, if the system yes, this is given as to be h or s, which performs on certain properties like on the x of t and giving the output y of t, what is the relation between this x of t and y of t? So, if x of t can be obtained back from y of t. So, you have given an x of t and you get the response as y of t. So, for a given y of t, that is the response what we obtained, from which we can get back this x of t, okay, the corresponding input, then the system is called the invertible system. So, you can get back this x of t from y of t. It's possible, that is going to be the invertible system. If it is not, so if we are not able to get the x of t back from this y of t, then it is going to be the non-invertible system. So, x of t can be obtained from its y of t for all possible inputs. So, that is the case which needs to be noted. So, it is not for one input you get a y of t, and then from y of t you can get back x of t, not for only one input. It should be valid for all the possible inputs. So this case is it is possible for every input. It is essential also for every input should have a unique output, that is one-to-one mapping. Each input x1 should have y1, then y1 should give back x1, x2 this should be that y2, and y2 should give back this x2. So this is an unique mapping, or the one-to-one mapping should be obeyed by these invertible systems. For example, we see y of t equal to x of t absolute. So, this if we take x of t can take positive or negative also here. So, if it is negative also, this would be y of t, and if it is positive also, magnitude of it would give y of t. So, this absolute taking the absolute of x of t, it is non-invertible because it is not one-to-one mapping. So, this y of t can have same value for multiple x of t's. So, x of t, suppose it is positive and was negative, because of this absolute one, it would give the same y of t. So, this is non-invertible system. Whereas again, one more example of y of t equal to x square t, in which this x square t, again if it is -1 for example, then x square t it is going to be 1, and if it is +1, again this would be y of t. So, you can y of t can have same value for two different inputs. It is not one-to-one mapping. So, this is called the again non-invertible system. We can, and y of t can, if you take 1 and get back the input, this can be -1 or +1, we will not be able to get it back. So, that is this is called the non-invertible system. And the case of the system which is invertible, let us take ideal integrator, the integrator which is ideal, and ideal differentiator. So, these are this is going to be the invertible system. So, you can integrate it, and from here you can get it the signal x of t can be differentiated, get s of si, and then integrated back, you can get the original input. So, the integrator and differentiator, this combination should have the invertible systems. Now, x of t and getting y of t through the system, and this y of t passing it to the inverse system, get back x of t. So, this is just a block diagram representation of this invertible and non-invertible systems. If this x of t we are not able to get it here, and this is going to be a non-invertible system. And if we take the stable and unstable systems, in which the stability of the system can be defined in two different types of stability. One is that the system, if it is given bounded input, then it produces the bounded output. That means the input should be a finite, it should not be growing like it going to infinity, and the output should not also be for a particular bounded input, it should not growing or going to infinity. So, the bounded value would result in a bounded output, that is called the bibostable external stability. So, that is due to this stability is defined due to only the input what is applied to the system, for which if the input sequence is bounded in the sense, then all value of n, that in which this the x of n, which is amplitude of this amplitude is actually making all negatives, the magnitude of it is bounded less than or equal to bx less than infinity. So, this should be this is called the bounded input, and it would result in bounded output. This is also an absolute value y of n and less than or equal to by less than infinity. So, this bounded input results in bounded output. The condition is given for all values of n. This is about the external stability. So, when we talk about this internal stability, in the sense that a system whose little more details about the system needs to be known, in the sense if the system's poles and zeros. So if all the poles of this system or the characteristic equation roots or roots of the system is going to be lying on the left half of the S plane, then it is called the asymptotic stability or the internal stability. So if the poles are lying on the left half of the S plane, we know that the system is stable. If the poles are lying on the JY axis, then those systems are called the marginally stable. If the system poles are lying on the right half of the S plane, then that is called, the system would be unstable. So in this case, what we are talking about, this internal stabilities, that's all the poles should lie on the left half of the S plane, that is called the asymptotic stability or internal stability. So internal stability is also due to this initial conditions. So if the internal stability is assured, then the system, for all initial conditions, wherever it starts, it would come to a decaying uh, output values. So that's due to the purely depending on the poles of the characteristic roots of the system. But external stability is something which is different from the internal stability. This is due to the input which is applied. Okay, so the Bibo stability doesn't guarantee internal stability. I mean, when the system is applied with some input and it is giving bounded output, that is Bibo stable, but doesn't tell anything about this internal stability roots of the system. Okay, so it is not guaranteeing, the external stability doesn't guarantee this internal stability here. Whereas internal stability, if the poles are lying on the left half of the S plane, yes, definitely that system is going to be stable. For it would also assures or implies the external stability. If the system is internal stable or asymptotically stable, then it would also assure the external stability, but the other way is not true here. So the example of this table, and if the unstable and stable systems, for external stability, similarly instability can be said like, for the bounded input, the output is not bounded. Okay, it's going to infinity, then this is not stable, not Bibo stable. Okay, so the example, y of t equal to x square t, in which that Bibo stable, this is before this, so those is just x square t, this is a Bibo stable one. So we come to the, after classification of this system, so we would see the system responses. So how do we have the system response, in which the linear system we have just referred in the previous lecture, there are two independent causes for the system response. So those causes, what are those causes? So we said when one is due to the input, another is due to the initial conditions. So the system response has two parts. One is one response part, one is due to the input, what is applied to the system, and other one the response due to the initial conditions. So when we say the zero initial conditions, the input is applied, only input is applied, then what is the response? Okay, zero initial conditions. And the other category is when the zero input, there is no input applied, and the response is due to only initial conditions. Okay, so this is another response. So we have this is a zero input response, and this we call it as zero state response. So zero state response, in which that only input is applied, all initial conditions are zero. So we call this category as the zero state response, and then this is zero input response. The input itself is zero, so there is no input applied, the output is only due to the initial conditions of it. So the y of n would contain both these two things. So the one input and the initial conditions would have both zero input response and zero state responses. So combining the two would give the response here. So now how do we find this zero input response and zero state response of a discrete time system? So usually the discrete time systems are given obeying a difference equation. So from this difference equation we can find out through the Z transform that we will see later, and taking the difference equation of the discrete time system, and this LCCDE, what we mean here is this linear constant coefficient difference equation. So that's that difference equation of the system will take and find out what is the zero input response and what is the zero state response. So these two responses combine and give the system response. So consider an example here, y of n plus y of n minus 1 minus 6 y of n minus 2 it's equal to x of n. The system equation obeyed by this is that given over here, that is the difference equation. So, x of n is the input and y of n is the output. So, we can take directly the z transform as well to get the y of z by x of z, which is the transfer function. So, if you take the transfer function, then you should consider them that the initial conditions are 0. Okay, so here, so the thing is here for a step input x of n equal to 8 u of n with initial conditions. So, initial conditions here y minus 1 is equal to 1 and y of minus 2 equal to minus 1. So, this is the given system with the initial conditions and x of n is the input. Input 8 u of n meaning the step response we have n and this is u of n. Here the amplitude of this is 8. So, this would continue up to n. This is the x of n, its equation. It have the 8 as the amplitude for the step input with the initial condition. For this, how do we find the 0 state response and 0 input responses? So, first step is to get the characteristic equation. So, substituting this y of n equal to lambda power n. So, you can have this lambda power n and the lambda power n minus 1 and lambda power n minus 2 and take the common ones lambda n minus 2. So, you get lambda square plus lambda minus 6 which is equal to 0. So, the characteristic equation of this difference equation is this, and solve this characteristic equation and get the lambda. So, here these are the roots for this equation is minus 3 and 2. So, these are distinct roots. So, in the if you recall the difference equation solving, we have the complementary solution and the particular solution as well. So, the complementary solution for this yc of n equal to, because of the distinct roots, alpha 1 this is a constant 1 minus 3 power n plus alpha 2 2 power n. So, what we get alpha 1 and alpha 2 needs to be found for this to get the complementary solution. This is one response. Complementary solution is one response where the roots are distinct, and this form would be different for the roots if it is repeating or if it is a complex conjugate. The formation of this complementary solution would be solution of differential equations. So, this alpha 1 minus 3 n plus alpha 2 2 power n, this is one response. Okay, so, next one we will go for the particular solution, that is we find the what is the response due to the input. When we have taken this characteristic equation, we have made this x of n not into consideration, this is 0. Okay, so, only the characteristic equation has this part output response. So, there is no input is involved in that. So, when we take the particular solution, the input x of n should be considered where it is going to be 8 u of n. The particular solution formation, this form yp of n equal to k is different for different type of inputs. So, okay, we can follow this as we have a few popular particular solutions can be found. What is the yp of n for sinusoidal inputs? What is the yp of n for constant inputs? So, a few forms can be learnt to get the particular solution. So, this is a constant u of n which is going to be 8 all the time where n is varying. So, we get this taking this yp of n as k. So, substituting this yp of n in the difference equation, that is equal to k. So, the first one y of n plus y of n minus 1 minus 6 into y of n minus 2, y of n minus 1 and y of n minus 2, all of them are k. So, equal to the input 8 u of n, that is this is going to be u of n is 8. So, from this find the k, that is equal to minus 2, k is equal to minus 2 from here, 2 minus 6 k which is equal to 8. So, after finding this k, what is the total solution? So, complementary solution and the particular solution. So, we added summation of these two is the solution of this difference equation y of n is equal to alpha 1 minus 3 power n, this is the one root, plus alpha 2 2 power n and minus 2 k plus k is the particular solution. So, this is the complementary solution and this is the particular solution. So, this is valid for n greater than or equal to 0. Now, still it is not complete because alpha 1 and alpha 2 is unknown here. So, for a solution system response, you need to know alpha 1 and alpha 2. So, how do we find this alpha 1 and alpha 2? So, we can get This simply here using the initial conditions in y of n, you can get two equations, y of minus 1, n equal to minus 1, y of minus 2. So, we can get two equations and we can solve alpha 1 and alpha 2 to get the total response. That is possible. The aim is to find here to zero state response and zero input response. So, taking this equation, this is for total solution. So, now we will find out the zero input response first and then the zero state response. So, zero input response in which with zero input and initial conditions, this is for the complementary solution. So, the input is 0 to find out the zero input response. So, the x of n should be made 0. So, what is the equation which we got? Y of n plus y of n minus 1 minus 6 y of n minus 2, which is equal to x of n. Now, we get substituting this n equal to 0 in this equation, n equal to 0, you get y of 0 and pushing all this to the right hand side. So, y of n equal to 0 would result in minus 1, and this is 6 y of minus 2, and here is the values what we get. For y of minus 1 we had the initial condition, and from minus y of minus 2 we get 1. So, this is going minus 1 minus 1 it is getting minus 7. So, these values are substituted from the initial conditions, so getting minus 7, and similarly substituting here y of n equal to 1, that is n equal to 1, and getting this, when it is 1 this becomes y of 0, and n equal to 1, this is y of minus 1. So, y of minus 1 is known, that is going to be 1, and the case of y of 0 what we obtained here, this is minus 7. So, get this 13. So, 0 and 1 we have two equations here, 0 1. So, the complementary solution which is the zero input response, the one which we obtained in the previous slides, that is complementary solution plus particular solution. So, taking only the complementary solution. So, the complementary solution is only due to the initial conditions, that is not the about the zero in that is there is no input in it. So, y of n equal to alpha 1 minus 3 power n plus alpha 2 2 power n. So, taking this equation and getting this n, substituting here n equal to 0, we get y of 0 equal to alpha 1, this becomes 1 and 0 plus alpha 2. So, we get one equation, and then substituting y of 1 here would have alpha 1, that is minus 3, plus alpha 2, this is going to be 2. So, we will have two equations here. So, this is y of 0 is substitute over here, and y of 1 substitute over here, and what we get, solve this equation for alpha 1 and alpha 2, which results in alpha 1 as minus 5.4 and alpha 2 is minus 1.6. So, this is the zero input response where we have not considered this x of n at all. So, that is going to be 0, the step input is not considered here. So, x of n is 0 over here. So, this is zero input response. So, what we did is taking the difference equation and using the initial conditions, we have obtained y of 0 and y of 1, and taking the complementary solution and so getting alpha and alpha 2. This is the response which is due to only the initial conditions, that is n greater than or equal to 0. There is no input involved in it. And the zero state response, which is with zero initial conditions and input is applied, that is a particular solution, that is we have to focus on the particular solution in this case. So, we take the difference equation and it is equal to x of n. Let us note the difference between this finding this y of 0 here in the zero state response and the case in which the zero input response, how did we find y of 0. This x of n is now taken into account, that is x of 0. In the case of previous one, if you look at it, this x of n is made 0 here, you can see that, and here now x of 0 minus y of minus 1, if n is 0, this is 6 y of minus 2, and these two values are known, that is initial from the initial conditions, and this is going to be x of 0 simply, which is equal to 8. Okay. So, these values, so y of 0 is equal to x of 0 here, and then y of 1 is x of 1, similarly y of 0, what is that, 8, this value is coming here, and these are y of minus 1. So, what are the values we have substituted for y of minus 1 and y of minus 2? it's not the initial condition value. So, we have to put this 0 here, this is also 0, that should be noted. So, these known values we have not used it for in the case of 0 state response. Okay. So, y of 0 is 8 and y of 1 gives the 0 over here. So, these two values are different from the y of 0 and y of 1 with the same equation what we obtained in the previous case. So, now using this y of 0 and y of 1, we will take the equation, that is y of n equal to the total solution alpha 1 minus 3 for n plus alpha 2 n minus 2. In this we compute this n equal to 0 and use this y of 0 and n equal to 1 and use this 0 over here. So, what we would get here, y of 0 equal to 0, this is alpha 1 plus alpha 2 minus 2, and when it is y 1, it is going to be alpha 1 minus 3 plus alpha 2 into 2 minus 2. So, solving these two equations for alpha 1 and alpha 2, 3.6 and you get 6.4 here. This is this 0 state response, whereas the previous one was this 0 input response. So, this is only considering the input what is applied to the system and also considering the initial conditions 0. Okay. So, and we will note that this is the total response what we got in the previous case, complementary solution. This is the complementary solution plus the particular integral is used in the 0 state response, whereas for the 0 input response, we made the input 0 and use the initial conditions, the response due to initial conditions, for which only the complementary solution is used. So, if we combine this 0 input response and the 0 state response, adding them together, then we get the y of n, the total solution. So, LCCDE difference equation, the system equations would contain the total solution which is having the 0 input response and the 0 state response. So, y of n would have 0 input response as well as 0 state response. You can check this adding the two, get the y of n, and if you recall that y of n equation is there, in that if you make the initial condition applied also and input both applied, and you can get this directly as well, instead of having getting this is 0 input response and 0 state response separately and adding it together. So, this is the total response which contains 2. So, just to demonstrate that this solution contains the 2, and you can find out separately and adding it to get the total solution. So, we can, from this case of 0 input and 0 state response, complementary solution and particular solution, from this we can also obtain not only the total solution, we can also obtain the impulse response. How are we going to obtain the impulse response for it? So, suppose what is the impulse response of the system? So, the system which is taking the impulse input, if a system is given an impulse input and the response is going to be this impulse response, which is often represented as a common notation h of n. So, h of n is the impulse response. This is the impulse input del of n. So, for filters kind of thing, the impulse input is going to be the impulse response. The impulse response itself is the coefficient of the filters. So, we would be using this h of n as filter coefficients in filter designs. Okay. So, the impulse response is very important to know for the system how to obtain the impulse response. So, when we take this LCCDE with impulse input, so the input for the example which we took, y of n plus y of n minus 1 minus 6 y of n minus 2 equal to x of n. To get the impulse input, this x of n should be del of n, that is impulse input, then this is going to give a h of n. So, for which the h of n what we got here is alpha 1 minus 3 power n plus alpha 2 2 power n. So, if you recall that this is nothing but the complementary solution. So, that complementary solution what we got is this impulse response. We will not consider this initial conditions, any of this here in this case, in this impulse response one. So, now if x of n, what is x of n? It is del of n. So, the complementary solution is obtained. After that, this x of n is going to be the input. Now, we get h of 0 from this. Okay. So, h of 0 is 1 and h of 1 is minus 1. So, if we get this h of 0 and h of 1, and then get this h of n alpha 1 and alpha 2 values. So, alpha, if we put h of 0, so here the what are the alpha 1 plus alpha 2, this is one equation, and h of 1 would get alpha 1 again minus 3 plus alpha 2 into 2. So, we get these two, and getting 1 and minus 1, the h of 0 and h of 1, we can get the h of n from this. Solving this two equations would get alpha 1 and alpha 2 here. Okay. So, but h of this input x of n is delta of n, which is valid only here at n equal to 0. This is delta of n. So, this is an impulse response of it, which can be obtained from the complementary solution, but you taking the complementary solution equation and find out this alpha 1 and alpha 2. Okay. So, if take this one with the initial, this needs to be found h of 0 and h of 1 for these cases. So, now coming to the convolution sum. So, LCCDE we have solved, that is getting the 0 input and 0 state responses and total solution. For any LTA system, that is linear time invariant system, what is the linearity property or what is the time invariance property we had seen. So, for LTA system, to get this impulse response, how do we get that? Or if for a given input, if we know the impulse response, can we get the response of the system? So, these things can be obtained through this convolution sum. So, let us see that what is convolution sum. So, the y of n, the system y of n is equal to h of x of n. So, that means this h is acting on x of n. If we take x of n is a discrete time sequence. So, this discrete time sequence, any x of n can be written as sum of shifted impulses. So, for example, that is if x of n is there, and how do we write it as an shifted sequence? The x of n equal to k is varying from minus infinity to plus infinity, x of k plus del of n minus k. In the sense, we have a sequence n, this is, let us take x of n, suppose this is 2, 1 and 3 is equal to 0, 1, 2 and 3. Let us take again to 4, and this is something like value 3. So, this is the sequence. So, this is the x of n. So, how can we represent this sequence as a shifted impulses? So, the k equal to 0. So, if I put k equal to 0 here, suppose we have this, let us take it as 0 in the negative indices, time indices, x of 0, and this is going to be this one, x of 0, which is 2, and del of n plus, you see x of 1, that is 1 into del of, this is n minus 1, this is a shifted impulse, plus this one is 3 into del of n minus 2, plus at this point it is 2 del of n minus 3 plus 3 del of n minus 4. So, like this, this signal is x of n now. If you take, this is the del of n, which is defined only at n equal to 0, then at n equal to 0, this is 2 into del of n, and this sequence at n equal to 1 is del of n minus 1. This signal, this impulse is shifted once, and the second one is, it is shifted twice, del of n minus 2, and then next one is shifted n minus 3 to 3 times, and then or n equal to 3, and 4 is n minus 4. These are the shifted impulses. We can consider and sum them up, all the shifted impulses, not only just shifting and multiplying this with the original x of n, what is the amplitude of it. This 2 into del of n, 1 into del of n minus 1, 3 into del of n minus 2, and 2 into del of n minus 3, and 3 into del of n minus 4, plus if you have some more sequences, then you can add them together. So, x of n, that is what this equation says, that any x of n, any sequence, discrete time sequence, can be return in terms of summation, k is infinity, minus infinity to plus infinity x of k del of n minus k, and that is called the weighted sum of basis function. The basis function is this del of n. Okay. So, this is the way in which we write it. So, replacing x of n in this equation, that x of n with this expression, um, then what we get over here. So, the y of n equal to h of minus infinity to plus infinity x of k del of n minus k. So, the x of n is now replaced with shifted impulses. Now, what h, can it act on this constant or can it act on this impulses? So, okay, so this is going to be a simply constant. So, this constant is taken out. This would act on the impulses. So, y of n equal to this x of k, and this is just a summation of h acting on is del of n minus k. So, this is going to be that h when system acting on the impulse input is impulse response, right. So, h of n minus k. So, this summation now results in this is retained, this del of n minus k, where it is acting on the h is acting on del of n minus k, which it's this, and when the system acting on impulse input is going to be an impulse response. So, x of k in h of n minus k, this is y of n. So, this summation k is varying from minus infinity to plus infinity, x of k h of n minus k is the convolution sum. So, this is an impulse response of the shifted responses. So, what we can say up from the convolution sum is that y of n can be obtained from this y of n equal to convolution of x of n h of n. We can say this is the operator which is replaced with the convolution. This is a convolution symbol, that is asterisk we use, x of n asterisk h of n. So, if we know the impulse response of a LTI system and the response of that system for any input x of n can be obtained by convolution sum. That is what we conclude from here. The convolution sum, if you know the impulse response of this LTI system, then any input response can be obtained by convolution of these two, h impulse response and x of n, we get this y of n. That is the sum over here. So, to conclude, we had seen the discrete-time systems properties of the linear and time invariance property, and we had taken the discrete-time system which can be represented with LCCDE, linear constant coefficient difference equation. So, by knowing the difference equation, we can find out zero input response and zero state response, which is the total solution or the total response of the LDI system. So, in this case, when you take the zero input response, that is obviously make the input 0, what is the response due to the initial conditions. When we take the zero state response, make this response due to the 0 initial conditions, that is called the zero state response. So, how do we obtain for that discrete time system? We had seen with one example. We can also obtain the impulse response by considering only the particular solution. So, by using the characteristic equation, and h of n can be obtained from that impulse response also can be. If we know the impulse response of a system, and we can find the response of the system for any arbitrary input which can be x of n. So, by representing this x of n as a shifted impulses of weighted sum. If we know that these details of the convolution sum, how to apply it for a system, we can find the response of the LTI for any input. Thank you.